So today I'm going to be showing you my online database for quantum error correcting codes. And before I do that, I would like to talk about my project's motivation. What is the purpose for creating such an online database? Well, quantum information theory is a growing field and has the potential to make transmission of data more secure and more accurate. Error correction, as its name suggests, refers to correcting errors found in messages when they are sent over some channel. And a quantum error correcting code over some field q squared has three parameters which determine how good the code is at correcting errors. Researchers in coding theory attempt to find record-breaking codes with best parameters. So what is a code with good parameters? Well, one way you can find a best known quantum error correcting code is by fixing n and k and attempting to find a code with the highest minimum distance. Or you can play the same game by fixing n and d and try to find the quantum error correcting code with the highest dimension, k. To show you how a researcher in coding theory could use my online database to search for best known codes. And a researcher would want to do this if they are running searches for best known quantum error correcting codes and want to know if codes that they find are record breaking codes. In order to know whether you have found a record breaker, you have to be able to compare your code with what has already been found. So we see that there are three inputs, Q, N, and K. By default, we fix parameters N and K and search for the quantum error correcting code with best minimum distance. So let's give this a try. We input the parameters Q is 3, N is 3, and K is 1. And we see that the result is a 312 over GF3 squared quantum error correcting code. We also see that we have a link to the paper in which this code was discussed. So why don't we open that link? So this is the paper, and when you open the link, sometimes it's not easy to access the actual paper. Sometimes you have to have some sort of a subscription or membership. So one way to get around that is by copying and pasting the link into scihub.se. And just like that, we have access to the paper. And we can confirm at the bottom that this code is in the literature, 312 quantum error correcting code over GF3 squared. And if a researcher wants to study the construction of this code, the theory behind this code, they can read this paper. By default, my site allows users to search by fixing N and K, but we can also search by fixing N and D. So why don't we run a search based on this criteria? we see that the result is a 4228-4 code over GF17 squared. And again, we can verify this code in the literature. You can scroll down and we find the table where the code is. We verify the parameters 4228-4. And again, if a researcher wants to learn more about how this code was constructed, they can simply read this paper. In both cases, the result is a single code. While this can be useful in some cases, it is also useful in other cases to be able to search for more than one code at a time, to search over a range of parameters. So to account for this, my database allows users to search by range over a range of n and over a range of k. So why don't we run a search with this criteria? Can input a lower bound here on n, an upper bound, and the same for k. Click search, and now we see that the result is a list of codes, each with a reference to the paper in which the code was found. Another important consideration when creating a database like this is to account for invalid inputs. So far, we have only seen valid inputs, but what happens if a user inputs parameters that are invalid? For example, all of these parameters, q, n, and k, must be non-negative integers. If we try to click search when q is negative, we see the message inputs must be positive integers printed to the screen. Another condition is that dimension cannot be greater than the length. If we input a k value that's greater than the input n value, we see this message: length must be greater than dimension and minimum distance. Also, when searching by range, it makes intuitive sense that the upper bound must be greater than the lower bound. So if we input upper bounds that are smaller than the lower bounds, we see this message printed to the screen. In addition to being able to search for best-known quantum error correcting codes, it is also useful for researchers to know theoretical bounds on minimum distance. This way, they know what they are searching for. Rather, they know what they can and cannot search for. And I'll show you what I mean by that. If we click on this here, we see a table. The horizontal axis represents dimension, and the vertical axis represents length. And the table is for codes over GF5 squared. Over here, we see an entry in the table. And what this means is, given a code with length 7 and dimension 1 over GF5 squared, the highest that minimum distance can be, theoretically, is 3. And if we click on this entry in the table, we are sent to the paper in which this bound was discussed, and we can verify this bound. Throughout the table, we see that many entries are missing, and this is due to a lack of data. As I continue to work on this project, I continue to update my database and filling in missing entries in this table. And we can see the same over these fields: GF7 squared, GF11 squared, GF13 squared, and GF17 squared. Thank you for taking the time to watch this video on my quantum error correcting code online database. I wish you the best of luck in your search for best known codes.